So let's just do it. Hey, welcome to the Weekly Space Hangout for Friday, September 25th, 2015. My name is Fraser Cain. I'm the publisher of Universe Today, and we have got another special guest all-star spectacular episode of the Weekly Space Hangout, where we're going to be talking to Maggie Scholtz from NASA JPL about drilling rocks. So I'm going to start with saying hello to Maggie. Hey, Maggie.
Hey, Fraser.
Welcome to the Weekly Space Hangout.
Thank you.
We've also got Dave Dickinson. Hey, David.
Hey, back here in Florida for a bit.
Awesome. And you're not going to sleep for the next 3 nights, right?
No, this is busy season. This is Eclipse weekend, so.
Yeah, you're so excited and terrified about the blood moon hyper super.
I'm more terrified of clouds.
Oh yeah, me too. West Coast to Canada. There's no chance I'm going to be able to see this thing, even though it's perfectly situated for me. We've got Morgan Rehnberg. Hey, Morgan.
Hey, Fraser. I'll be sleeping pretty soundly, I think.
You're bored of lunar eclipses now.
So jaded.
So jaded. We've got Paul Sutter. Hey, Paul.
Hey, how's it going?
Good. Welcome back to your second regular episode of the Weekly Space Hangout. You are now a veteran. You are really a veteran. Wow. Yeah, we're going to give you your astronaut wings shortly. I'm not sure how this works.
Sweet. Is there like little service ribbons for certain kinds of guests? And
yeah, exactly. Yep. So we're going to be talking about today all kinds of good stuff. Of course, we're going to be talking to Maggie about what it's like to deface the surface of Mars in the name of science. We're going to be talking about colliding black holes, what's up with Martian dust storms, which I'm hoping Maggie's going to have lots of opinions about. We're going to be talking about, of course, the total lunar eclipse that's coming up on Sunday. I am, in theory, although, obviously with the clouds, I won't get a chance to see it. Exoplanet, actual photograph of an exoplanet, actual video of an exoplanet, more amazing pictures from Pluto, and an update on science from Rosetta, and perhaps a couple of other science stories if we have time for them. So let's get on. So just to remind you, this is a live show. We are happy to interact directly with you, our beloved audience, and so the way you do that is use the Q&A app. So wherever you're watching this video on YouTube, you're going to see a little bar at the bottom of the page, the screen. Click that. And then you'll still be able to watch the video, but now you'll be able to answer, ask any questions that you want of any of the panelists, as well as our special guest. So I'm going to say hi to Guido Bibra and David Dunn and Richard Clark and Alexander Howlett and Sylvan Westby and Tony Lynch and Richard Drum and Jim Meeker, Nancy Graziano, Leonard Lindstrom, Matt Woods, Giselle Sabarin, Ignatiy Romanov Cherengovsky, Bert Wolters, and I think, Joe Reichel, Linda Sadek. There's a lot of people now. Rick Schwartz, Thomas Straniker.
New names.
I know. Elliot Avron, yeah, Tom Nathy, and Paul from astronomynj.com. Wait a minute, Paul. Did you just advertise inside the Weekly Space Hangout? Nicely done.
Very clever.
Very clever. But yeah, go ahead, post any questions that you want, and then as we kind of move into the conversation, we will answer them. So I was told to parade some Parsec Awards in front of you. So there they are. 2 Parsec Awards for the Guide to Space for 2014 and for 2015, and now I can display them shamelessly. So let's get on with the episode. So Maggie, welcome to the Weekly Space Hangout. Can you give everyone a brief introduction of who you are and what you do?
Sure. So my name is Maggie Scholtz. I've been working at JPL for about 6 years now, and my main job is developing the hardware that actually goes to Mars. I've worked on the Curiosity mission for about 5 years or so, a few years before the mission actually launched, and then a few years afterwards as well. And I'm now working on the Mars 2020 mission, which will be a very similar rover, also landing on Mars, where we're going to be making rock cores.
So let's talk about the kind of hardware that you've been working on. If I recall correctly, right, on the Spirit and Opportunity, they had the rat system, right, which was like this grinder that would grind these little holes. So what does Curiosity have as a sort of drilling system?
Sure. So Like you mentioned on MER, we have the RAT tool, and the idea is that you take away the weathered surface of the rock, and then you take the science instrument that's on the end of the arm and place it right up against that surface. We do something very different on MSL. We have a powdering drill. It's a rotary percussive drill with a drill bit that you can buy from Home Depot. And we make powder out of the rocks, and then we take the powder and move it through a labyrinth system. We sieve it so that the particle sizes are down to a level that you can that the science instruments can accept, and then we drop off a very tiny amount into one of two different science instruments on board on the rover, and then those science instruments take that powder and analyze it for what the composition is.
And then the rover poops it out.
The rover actually keeps it. There's no rover pooping involved with this mission.
Not yet or not ever, because I thought I was talking to Emily Lockdewalla, and she said that eventually it will poop out some of its samples out onto the surface of Mars.
So let's see, the Curiosity mission, they do have the ability to drop the powder that has been analyzed, but that powder will actually stay inside of the rover. It just drops out into a tray, and then when we're actually sampling, after we drill into a rock and collect the powder and have gone through all the science that we want to do, we do drop off, we call it drop off, all the powder that we're not going to use onto the ground. So maybe there's a little bit of pooping there, but.
Well, I just imagine in the future some, Mars astronaut who's desperately trying to survive on the surface of the red planet will be able to follow this trail to follow and find Curiosity down the road.
Actually, the next mission will.
Oh, right, okay.
Yeah, so the one that I'm working on now, Mars 2020 rover, we make rock cores, and then the cores go into a tube that gets sealed, and then we will actually be pooping these cores out of the rover onto the surface of Mars to be picked up by a later mission. And there's some descriptions that you can find online of that process. And we do leave a little bit of a trail of breadcrumbs that the future mission would have to come back and follow that trail of breadcrumbs to pick those samples back up off the surface.
So in the case of MSL, you've got this powder that you're able to study and get some of the material out of it. What does the core give you?
So the core, we don't actually we don't analyze the core on Mars. The purpose of the core is that we preserve both the composition of the rock and we preserve the stratigraphy and the order of the different particles within the rock. So you can get some history from looking at the rock. You can see the different layers, distinguish between the different layers within the rock that you get back. So there's a lot more that you can learn from having an intact core. And those cores would actually be analyzed only on Earth. We can look on the Mars 2020 mission, we'll be able to look inside of the hole to look at what the wall of the hole actually looks like, but the core itself will not get analyzed until it comes back here.
Oh, that's interesting. So the rover itself won't have the capabilities to really analyze what's in the core. It would take a trained geologist to be able to do that. So what would that sort of sample return mission look like?
I'm sorry, you cut out. Can you repeat your question?
Oh, sure. What would the sample return mission how would that work?
Well, so the Mars 2020 mission I mentioned, it effectively ends at dropping off the cores, and creating the cores is not the only part of that mission. It's just the part that I focus on. There's a lot of other science instruments happening on there, but there would be multiple future missions that are required in order to bring the cores back. I probably will, some of my friends will tell me that I'm going to describe this slightly wrong, but the general idea is that we land something on Earth that's another rover that will drive to those locations, pick up those rock cores, and then go back to the thing that landed we call the MAV, which if you have
the Mars
already
Ascent
read
vehicle, yeah.
The Martian, very similar.
Yep.
that will leave Mars, go into orbit around Mars, and then a separate mission will grab the cache of sample and bring that back to Earth. We'll drop it on the ground, and then the scientists will take those cores into a very very well contained facility, and they will take thin sections and slivers of these cores to run their analyses on.
So you're an engineer by training and practice. What is different about designing hardware for Mars than maybe designing something that maybe would get used here on Earth?
I would say the biggest difference is that the whole point of the mission in the first place is to learn things that we don't know about. So we don't know what the rocks are going to be that we're going to interact with. We take some very well-educated guesses about what the materials will be, and the engineers here work with the scientists to figure out what types of rocks we might be encountering, but ultimately we are guessing. And so in order to build a drill that will be able to function in all of these rocks of these properties that we don't know for sure of, we have to be able to build it for a whole wide variety and spend a significant amount of time testing in this wide variety of rock materials in order to do that. Sometimes we take the rocks, a lot of the samples we go into are rocks that we've collected on Earth. Sometimes we create ones ourselves because there's nothing on Earth that exists because they were formed in a different environment. And sometimes we take the rocks that are on Earth and try to alter their properties in some way in order to put them in a more Mars-like condition.
And is there any kind of, can you get any sense of what the wear and tear is on the equipment on the rover? Can you sort of take a look at its drill and see how it's doing?
Yeah, so we actually do take stock on a regular basis of how the drill is doing, how the hardware is doing. There are pictures that we take regularly looking at the drill bit to look for wear, because, you know, if, as any other drill bit goes, if you wear it too much, it's not going to work out anymore. And when that drill bit does dull and we can't use it anymore, then we will drop it, leave it on the ground, and we have two other ones right on the front of the rover that we can chuck onto the drill and keep going.
What's going to last longer, the drills or Curiosity's power source?
Ooh, I'm not sure if I can answer that question very well. I don't know enough about how much the power source degrades, but I believe the drill would probably wear first, because as the power source degrades, instead of just stopping function, we will just have a shorter and shorter amount of time each day that we can actually operate. And that process will take a long time to reduce how much power we can use every day. So I would guess the drill.
And eventually, I guess Curiosity won't be able to have enough power to really move anymore, and it's going to sit as a sort of as more like a lander, and then I guess it's just going to drill everything around it, like, you know, that it can find. So, have there been any like big surprises so far from some of the samples that people have done?
So I can mostly speak to the mechanical aspect of that over the science aspect of it, but I would say one of the biggest surprises is how soft the rocks are that we've been going into. You know, I mentioned that we tested on a really wide variety of rocks, and some of them are the really hard basaltic rocks that are from basalt flows, lava flows that have cooled. Which do exist there, we just haven't gone into them. We've been going into a lot of mudstones that have been very, very soft, and so in general, the Martian surface we've been going into has been very nice to our hardware.
That's good. Mars is playing along nicely.
Yes.
And of course, I think, you know, the work that you're doing with the rovers and with the drills on Mars, this is really setting the stage for drilling all the things, right? You know, there's plans for capturing asteroids and bringing them into orbit. What would be different, perhaps, about trying to create some kind of system that would drill an asteroid? Have you sat and thought about that, and have you got any back of the napkin math that you've worked on?
Yeah, so I haven't personally worked on other sampling missions, but the group that I actually work in here is a sampling mission or sampling group, and people in my group work on. They've tried out things for the Moon, for Venus, and the big thing that just changes is that the composition of the material that you're going into is going to be different. Mars is covered in everything on Mars is volcanic based. Even the mudstones themselves, it's just a bunch of really tiny volcanic particles that are bound together. Something like an asteroid or a comet, where the gravity is so low, we would expect, but we're not sure because we haven't actually. Besides some of the ESA missions, we haven't personally tried sampling any materials on an asteroid or comet. So with that low gravity, you would expect the material to be very fluffy. And so we actually have a lab here that creates materials based on different densities to try to sample some soft things and some harder things.
Yeah, and then of course the low gravity, like as we saw with the Rosetta mission, working in that really low gravity is going to be really tough. And I guess if you're going to be trying to drill on an object with very low gravity, that's a whole other engineering challenge.
Right, and so you don't necessarily drill in those cases if you're going to try to acquire a sample from something that's that soft. An example of a material that we have used in the past to practice with is that the green foam that you get at a florist, where they put the flowers into that foam. It's sort of it's a little squishy and it can crumble a little bit. We have actually used that material to test out some of our sampling techniques for comets.
So it's almost like a lint roller would work better than a drill.
Yeah. But they said the scientists always want to be able to preserve the stratigraphy as much as possible, and so you lose the layers when you mix it all together like that.
And so what about Venus? I mean, I can't even imagine the engineering challenges of getting something that could survive on Venus long enough to be able to gather a sample. So, I mean, what would be involved in that?
I think the biggest challenge with Venus is, like you said, being able to stay alive for long enough to be able to sample something. We have different different techniques that that people have been trying out, and the big target is to be able to find something, anything that works as fast as possible to collect things as quickly as possible, in order to collect it and then put it into the science instrument that can analyze the material. So something like a rock core, if you were to collect a rock core and then you want to put it into a science instrument, you probably have to crush it up, and that takes a lot of different processes. And so the techniques that we've been trying out for Venus are sort of like trying to dig out the rock material as fast as possible and almost throw it into the science instrument as quickly as possible, keeping everything simple so you can do it quickly.
And then the rover dies.
Yes, then the rover dies.
Or the lander. So, I mean, and again, we're probably ranging pretty far from what your expertise is, but it's okay to just, we're all friends here. Use our imagination. And so a lot of interest now is happening with places like Europa and Enceladus, which, more and more evidence is that these places have these gigantic under ice oceans, and they're potentially the best places pretty much in the solar system to search for life. Have you had any thinking about what would be involved to perhaps collect samples in places like that, where I guess when you think about places like Pluto, where the water is the ice is as hard as a rock, right? It's like the same technology comes in. So have you sort of had any thought about what would be required to work in those kinds of places?
So we actually have recently started spending a little bit of time trying to understand how to collect the ice very effectively. I haven't personally worked on any of the ice collection work, but I can allude to some testing that where we go into a material that we know has water in it, and if we ran a whole lot of tests that were at the in the Martian environment, so we would cool everything, effectively freezing the water on purpose in our test. And so one thing that would happen in this case is you would be going into the rock material and you hit the ice and you heat up the ice because you're drilling into it, and it could it'll sublimate. Mars in particular is actually, the environment's very close to the triple point of water, so depending on the day, it could either transition into water or straight to a gas. So when that happens, it's actually difficult for you to collect your powder if you're creating powder, because when you go from the solid to an expanding gas, it just wants to shoot all of the powder that you're creating out of the hole and away from your collection device. So trying to sample ice is very hard, trying to keep it intact as much as you can in order to preserve the material.
So I've got some questions from the viewers right now. So this question comes from Richard Clark. So what is the maximum drilling depth obtainable on a Mars rover? Is there a future plan to go deeper than that, and when? So how deep can the various rovers go right now?
So Curiosity goes about 6 centimeters down into the rock. Our Mars 2020 mission, the rock cores, will be of a similar depth. We're still trying to figure out what the right depth is, but it will be in that ballpark, possibly a little bit deeper. As far as the missions that I've been working on, that's as far as we're trying to go. There's a lot of limitations on how deep we can go because of how long it takes to actually drill into the rock. We want to be able to do it in as short a time as possible so that we can safely remove the tool from the rock during the day before it cools down and before everything wants to move around from the thermal changes on the rover. I believe that there's some ESA missions that have been looking at some deeper cores, but I don't really know much about that. So far, right now, we really just look at on the order of 6 centimeters.
Right. Someone would need some kind of crew of ex-oil drillers to go to Mars to go deeper.
Yeah.
Is the InSight mission going to drill? That's taking off here in a few months.
So InSight doesn't drill. They actually, I'm not aware of any sampling feature on InSight. I know they have their main thing is the seismometer that they're putting onto the ground, and there is an arm on that mission, but the purpose of the arm is to pick the instruments up off of the top deck of the lander and place them on the ground surface so that they can actually go in there and be directly in contact with the surface. There is one piece of it called the mole, which is, I believe, being developed in Germany. And there's a tiny device that tries to burrow deep into the regolith, and this is they're targeting landing on powder, on regolith material, and it burrows down and takes a whole chain of temperature sensors with it, and so it tries to go down a couple meters into the ground, bringing the temperature sensors with it to understand what the thermal gradient is through the soil.
Interesting.
So the next question comes from Alexander Howlett. What kind of background and qualifications should aspiring engineers keep in mind when thinking about a career with JPL? So what worked for you?
So I think one of the things that I feel like shocks people the most when I tell them is that I have a bachelor's degree and I don't have any degrees beyond there. So the idea that you have to have a doctorate in order to work here is fiction. I think of the engineers, at least within mechanical, about half of the people working here only have bachelor's degrees, and then the other half have masters, with a very tiny group of people who actually have doctorates. So I would, probably my biggest suggestion is just, if it's something that you want to do, just make sure that you're actively pursuing it. If you want to work here, make sure you actually apply. That's the first step. If you're interested, there's internships, and all of these offers are on the website. I would say that the reason that I got here is because I really wanted to come here, and I just kept trying, and I kept targeting every avenue I thought would possibly get me here, and then eventually one of them worked.
You just drilled holes throughout in front of NASA JPL. Some kind of mole person. Let's see. So this question comes from Tariq Karabesh. How will the 2020 rover be different from Curiosity? So, I mean, they're going to look very similar, right?
They are going to look very similar. We're actually we're using a lot of the architecture in the design of the rover itself, that we did for the Curiosity rover. In fact, some of the hardware that we're using was spare hardware that was built for the Curiosity mission. From an aesthetic point of view, the average person would probably look at both rovers and not be able to tell the difference between the two. The big difference is, I've already mentioned that the sampling is going to be very different, and we're going to be dropping off cores on the surface. And then we also have a whole new suite of instruments. Every instrument on Mars 2020 is brand new, did not go on Curiosity. I believe there's 10 science instruments. And so all the changes that happen to the rover from what we had on Curiosity are purely in order to accommodate these brand new instruments.
That's really cool. Let's see. I've got one more question from Elad Avron, which is, will the Mars 2020 rover be only a sample maker, or will it do some science itself?
So one of the requirements for the mission was that it can't be just a sample maker, and that it has to do science as well. It has to be a standalone mission that can't just depend on having future missions help make it successful. So like I mentioned, there's 10 science instruments on there. 2 of them are on the end of the robotic arm. So at the end of the arm we have the coring drill, and then there's also 2 instruments, just like we had 2 on the Curiosity mission, and we'll be placing them up against the surfaces. We'll have we're going to be doing something just like we did with the rat on MER, where we're braiding away some surface so the science instruments can get up close and look at the unweathered surface of the rock, and they'll be able to see the regolith and the top rock surface, and be able to look into the holes that we created with the cores a little bit. There's a bunch of other mission instruments on the mission that I don't know as much about because they're not strapped onto the side of the part that I'm working on, but I do know that there is one really cool technology proof, or actually we have 2 cool technology proofs. One of them is not yet approved, but one of them is called MOXIE, and the whole purpose of MOXIE is to prove out that we can take the CO2 out of the atmosphere on Mars and convert it into oxygen. The idea is that we can use this on future missions when we actually send people there. And then the second really cool technology proof that is not yet approved, but they're working on it, is the Scout helicopter. If you look, you can probably search online for the Mars Scout helicopter, and we're trying to put one on there that can fly away from the rover and look at what some of the cool rocks are that we saw from the satellite images, and see if it's actually something cool or that is interesting to look at, and if it's actually achievable terrain or achievable path for the rover to go on, and it'll result in us having a more efficient mission. And it's also really awesome because it would be a helicopter on Mars.
That would be fantastic. So why don't we shift gears now, and we'll sort of talk about the big space news this week. And Maggie, I know you want to stick around, especially some of these I think will be in your ballpark. So we'll definitely love to hear your comments on it. So let's start. We'll stay in the Mars realm here, Paul. And you're here to sort of break a few hearts as we're just about to watch The Martian.
Yeah, don't watch it because the whole movie is a lie.
Oh, like my life.
No, I'm kidding. I'm kidding. I'm gonna watch it. I'm really excited for the movie, actually. But the thing that kind of sets the story in motion is this big sandstorm that knocks over stuff and what they think they kills the main character. But the difficulty with Mars is even a very strong wind on Mars doesn't exactly impart a lot of force because there just aren't as many air molecules floating around to actually do the pushing. So actually, I'm curious, Maggie, how exactly will a helicopter on Mars work? Does it have to be super, super big?
Yeah, actually, in order to make it work, the blades are enormous as compared to the actual payload it's supporting. If you see some of the pictures, it looks like the part that's being flown around is about this big, and the blades are well beyond what I can show in my screen. And then they also spin much, much, much faster than a normal helicopter blade would in order to actually get enough lift. So it's effectively just a very, very powerful, very light helicopter.
And we actually did a video just recently on this on the Guide to Space, and if I remember, as I did my research, it's about 1/10 the force of what it is on, of what an Earth
roughly
wind
your
is.
hair, if you had hair.
Yeah, if I had hair, you couldn't fly a kite on Mars if you tried. Even in a howling windstorm, you wouldn't be able to even get a kite off the ground. So
I think Andy Weir on a recent Reddit AMA, he researched this book incredibly thoroughly, and he said he knew that sandstorms on Mars wouldn't be this powerful, but he just wanted something to get the plot moving, and that was the best thing he could think of.
He actually said that on this show. Last year. Yeah, as well, and absolutely, and we sort of gave him a hard time then, and then we gave him a hard time in the Guide to Space video, and we're giving him a hard time now. But Andy Weir, we totally get it. We love you. We can't wait to give you all our money when we watch The Martian.
And see, when I watch movies, I just pretend it takes place in a universe that is very similar to, but not exactly like our universe. So it's a Mars where the wind is actually strong.
You're a screenwriter's dream.
Every science fiction writer has one get out of jail free card when it comes to
okay.
So.
Yeah, exactly. But I mean, the rest of that book is so tight. So yeah, no argument here. Have you got one in yours, David? In your book?
Quite a few, actually.
Oh, okay. You only get one.
Per book. Oh, per book.
Per book. Yeah. Okay. All right. Morgan, let's talk about Pluto.
We can talk about Pluto every week from now until the end of time, it seems like. And we were just talking last week about some of the new amazing images returned by New Horizons from its Pluto flyby. Remember, all of these were taken on or around July 14th, and we're just slowly trickling them back to Earth. But we got an even more amazing set of images back this week. I'm going to show a few of them for you here. The first one that I'm not going to show is just a much higher resolution version of that full disk Pluto image. And if you haven't seen that image yet, you should go and find it and just zoom really far in, because you can see all sorts of amazing detail. But in addition to that really big image, they also released a series of close-ups showing some of the really varied terrain that we can see on Pluto. And this is one of the images that got the most attention, and it's been sort of described as looking like snakeskin. You can even pan around a little bit here. And you can just see this very, very fine scale detail of ridge and trough and ridge and trough, with some of these larger cracks that maybe we've been seeing from the orbital images, or from the much farther out images, superimposed on top of that. And remember, the surface of Pluto is made primarily of water ice, but there's also probably a layer of nitrogen ice on top of it. And we know that the large structures on Pluto couldn't be created by that nitrogen because it doesn't have enough strength, basically, to hold itself up. But some of these smaller scale features very well could be the result of sort of some strange nitrogen geology going on the surface of Pluto. I'll show a couple more here. Here's a nice sort of panorama of the surface that shows these are not in true color, but they're also not in sort of blatantly false color. They're talking about still developing the color model to understand exactly what colors represent what on the surface. But we can see that there actually are some craters on Pluto, something that large portions of the surface don't seem to have. But we can also see how this sort of mountainous terrain then bleeds into this much smoother terrain. And seeing a good close-up of this smooth terrain really sort of, I think, helps answer one of the fundamental questions that we had going into Pluto. And that's the first images we saw looked a lot different than we expected. We'd kind of expected that Pluto was going to look a lot like Neptune's moon, Triton, because we think Triton was once a captured Kuiper Belt object and likely had a history very similar to that of Pluto. But when we first saw Pluto, it didn't look anything at all like Triton. But now it's starting to. And one more zoom in here on this very smooth, kind of dimpled terrain. And this looks very similar to this next picture I'll show, which is an image from Voyager of Triton. And this is sort of the famous cantaloupe terrain on Triton, because it looks very much like the skin of a cantaloupe. And what we're seeing is that, yes, parts of Pluto do look like parts of Triton. But just like there's a lot of varied terrain on Triton, there's an incredible amount of varied terrain on Pluto.
Really interesting. So it's almost like by looking at the images of Pluto, the scientists are now able to go back and look at Triton and get a better sense of what kinds of features they're looking at.
Absolutely. Just like New Horizons, the images we have of Triton were taken during a flyby, in this case the flyby of Voyager 2. But of course, in 1989, when that flyby occurred, they didn't have nearly the same level of technology or experience that we did with New Horizons this year. And so while Triton kind of led the way for understanding Pluto for decades, now we're going to be able to use Pluto to help understand what might be going on at Triton.
So, Maggie, we mentioned this briefly earlier on in the show. Any thoughts on what it would take to drill into ice that's as hard as rock to see what's beneath?
Well, I think that it would be similar to what I described before. Given that there's very little atmosphere there, when you release the gases, if you heat up the ice enough that it will sublimate, then it will try to shoot all of the particles you're creating straight out of the hole that you're going into. So that would definitely present a difficulty. I know that sometimes in Antarctica, when they try to core down through ice, which is where a lot of research actually happens for coring in ice, they'll actually, instead of cutting into the rock like a drill would, they would heat it and to just create the actual core, just with a hot circle, and just kind of shove it down into the ice to collect the core.
And that's been proposed for use on Europa as well, because we're not going to be able to carry a many kilometers long drill bit to Europa, but we could carry some sort of heating element and drop it down slowly.
Drop a lump of plutonium on it and hope the Europans don't mind.
With a wire, yeah. With a microphone and a camera and a lump of plutonium, and just let it find its own way down into Europa. All right, well, let's move on. So, David, of course, this is it. This is the end of the Blood Moon Tetrad. This is the one that will. I forget. Is it going to look cool in the sky, or is it going to end the Earth? Which one of these is it going to be?
I think it's just going to put on a very good show Sunday night. It's placed pretty well for. And what's cool is people in Europe and Africa will see it Monday morning as well. And here in North America and South America, we're going to see the total lunar eclipse. Final one of the 4 set tetrad. There was 2 last year and 2 this year. And this is the final one till January 31st, 2018. We're going to actually have a blue blood moon in 2018, so that's going to be even crazier probably.
But isn't this a super blood moon?
Yes, this is a perigee moon and a harvest moon as well, so it's whatever flavor of moon you want to call it, basically. I did some research for the article I wrote for Universe Today about how common perigee moons are, or supermoons. Now, so the term supermoon is not really an astronomical term. It was coined by an astrologer a couple decades ago, but the internet's kind of taken it over.
Yeah. So we need to own it, David.
Yes, we've been working on it. The description I prefer for what I call a proxygean moon or a perigee moon is a supermoon, a full moon that occurs within 24 hours of lunar perigee. And looking through the 21st century for lunar eclipses that occur near perigee, I actually found 15. So they're not really that uncommon. You get one about 1 or 2 every decade or so. And this Saros cycle, incidentally, you get the 19-year Saros cycle of eclipses, is generating perigee eclipse moons. In 2033, about 18 years from now, we're going to have another one that's within about, this one is 1 hour and 5 minutes away from perigee. The one in 2033 is about 1 hour, 13 minutes away, so it's almost as close. This one, incidentally, this Sunday is the closest full total lunar eclipse to perigee for this century, but not by much, by like a few minutes. So,
on a diversion, can you explain what that is behind you?
Oh, that is my DSLR. That's probably what I'm going to actually be shooting the eclipse with, minus the solar filter mask on front. That is a Nikon D3200 DSLR with a 400 to 1200 zoom lens and a 2x teleconverter on it, and it gives you like a small refractor telescope with your camera. So it's an all right setup. As always, I would like to have better lenses and a better camera, but you know, I'm a writer, so.
Yeah, no, I'm just sort of tempted to bolt something like that on the front of my camera as well.
This will probably Sunday night, if it's clear. I'll have this piggybacked on the 8-inch that I use for the virtual star party, and I'll probably be doing video through the 8-inch telescope, and I'll probably be shooting stills on this one at the same time. So that's assuming it's clear. The forecast I see here, all of North America looks pretty clear Sunday night, except Florida is kind of a toss-up. So. But it says high clouds. You don't. Yeah. The cool thing about a lunar eclipse is you don't need a crystal clear sky. You just need a view of the moon. So if there's clouds, you remember in the virtual star party, we could still show the moon as long as there was clouds moving in front of it. And what's really cool with the lunar eclipse is, like meteor showers or aurora, you don't really need any equipment to watch it. You just go out and look, and there it is. So you just need a working set of eyes.
And so just one final reminder, right? Sunday night, if you're on the West Coast, the moon will be rising and pretty much go into eclipse. If you live, say, where Morgan does, in the middle of the country, it couldn't be more perfectly... Like, Morgan, you could literally sit on your couch, look out the window, and see the lunar eclipse. So I know you're kind of meh on these things, but this couldn't be better for you.
I'll do it for you.
All right,
we were talking earlier that not all total lunar eclipses are quite the same. It depends how deep. The Earth's shadow at that distance is about 3 times the apparent size of the moon. It depends how deep the moon goes in and how much aerosols in dust and particles there is in the Earth's atmosphere, which is refracting that sunlight onto the moon. The moon can appear anywhere from really, moon is almost, after the Mount Pinatubo eruption in '92, there was a total lunar eclipse, I remember. The moon almost disappeared. It was that dark. There's what's called the Danjon scale, which measures how the darkness and the redness of the eclipse, versus the eclipse we had this past April. Now, I didn't see it. I was in Maine and we missed it. But there was, the moon barely passed into the outer edge of the Earth's shadow, and the edge of the umbra, the inner core. And there was a lot of discussion about whether that was, although it was technically total, whether it was actually total. And I wrote about this a little bit on Universe Today. There was a big discussion about the estimated versus actual size of the shadow of the moon. So to a lot of, or shadow of the Earth, to a lot of observers, the moon didn't quite go dark on that eclipse.
All right, let's move on. Paul, let's talk about colliding black holes. Is that even possible?
Yeah, well, of course it's possible. There's a problem that we have. So every galaxy hosts a supermassive black hole at its center, and galaxies tend to merge every once in a while, and so the supermassive black holes ought to merge too. But what happens with black holes when you run this through simulations is they don't just crash into each other like a head-on collision. They come in at some angle or some different direction, so the black holes will actually tend to orbit each other. And we have a problem of how do we get black holes from just orbiting each other to actually merging together to form a single black hole that we see in the centers of all these galaxies. One possible answer is gravity waves or gravitational waves. So as these black holes are orbiting, they emit gravitational waves, and that kind of sucks momentum and energy out of the system and allows the black holes to get closer and closer together and eventually merge.
Right, and I know that this has been this has actually been detected. These gravitational waves have been detected by, say, pulsars orbiting one another, and they've been able to detect the energy that's being emitted from these pulsars, and that sort of decreases their I guess, angular momentum, and they pull together and then merge, right?
Yeah, so we don't have any direct observations or measurements of gravitational waves, but we see the effects of emitting gravitational waves happening out in the universe. But the problem with these supermassive black holes is that for the gravitational waves to actually have any significant effect, the black holes have to get to within at least a parsec of each other. They have to get really close. That's when the gravitational waves will be strong enough to actually draw them closer. And we don't know how to get the black holes from, say, 10 parsec or 20 parsec away down to 1 parsec where the gravitational waves will actually start to do their thing. So we call this the final parsec problem of how do you actually get the black holes close enough together where the gravitational waves will be emitted and they'll actually finally make the merger. And this is an open problem in astrophysics. And there's this article that came out, a group led by Zoltan Hyman. Have you had Zoltan on the show before?
No.
Oh, you should. He's a super cool dude. So they did these observations. They looked at a quasar, which is an active galaxy where the black hole is feeding, and they noticed that there's this periodic flare-ups in intensity coming from this quasar. And by looking at the modeling or doing some modeling, trying to figure out what could cause this periodic flare-ups, they think it's 2 black holes that are very close together, like 1/100th of a parsec, which that's close enough you can actually start using miles or kilometers to describe it, like billions of miles or billions of kilometers away from each other. And they're orbiting each other very, very quickly, and simultaneously both black holes are feeding on the gas surrounding them, and it's causing this the flare-ups in the observations. And so this might be an observation of 2 black holes that are very, very close together. And so by studying this system, and then now that we have the signature of this system, we can start looking for other ones in the universe. We can start to get a handle on what's going on when 2 black holes actually get freaky and get close to each other.
But that doesn't solve your final parsec problem, right? I mean, you still...
No, but it gives us some observational evidence. Like, here's a picture of 2 black holes that are within a parsec of each other. What are the physics going on here? We can start to model the physics and test them against these observations so we can develop some picture of what's going on.
I mean, at that point, do you have them sort of going through each other's accretion disks? Have you got, all kinds of three-body interactions going on that might be kicking them closer and further away from each other?
Yeah, it's bound to be a very complicated process because it's not just 2 black holes, just 2 points in space. They have accretion disks, there's gas, there's stars in the center of the galaxy that will be orbiting around and gravitationally interacting. It's a very complicated problem.
Yeah, absolutely.
In related news, Paul, Advanced LIGO just went online about a week ago. They're taking observations now, so they say the first gravity waves from those kind of direct detections are probably near Alpha Centauri by now. So,
oh, nice.
Within that range of the ones we're going to first get those first detections. So.
Yeah. Advanced LIGO is the gravitational wave detector experiment, and LIGO was the one that failed to find any gravitational waves, and then they've just completely upgraded the hardware on it. I think it's 10 times more sensitive.
Yeah, they just turned it online about a week ago. Both detectors are in sync now. So. And
pretty much if they don't detect a gravitational wave, then maybe Einstein was wrong at this point. So, okay, great. Well, let's move on. Let's see, Morgan. Let's talk about new updates on Rosetta.
Right. Believe it or not, the New Horizons is not the only spacecraft out there in space. Rosetta from the European Space Agency has now been in orbit about Comet 67P Churyumov-Gerasimenko for almost a year now. And despite troubles with its Philae lander, Rosetta has still been carrying out a lot of really great science. And one of the focuses during the period over the last few months when the comet was making its closest approach to the sun was understanding how sunlight and the surface interact to create sort of weather on a comet. And what they discovered is just like we have a water cycle here on Earth, the comet itself also has a water cycle, because it's kind of tumbling through space, which means that it's going day to night to day to night on any given location every few hours. And what happens is when sunlight shines on that surface, it heats up the surface, and that solid ice goes directly to water vapor, which we call sublimation. And that's different than here on Earth, where we tend to go from solid to liquid to evaporation to gas, and then it rains back down. And so then when it goes to nighttime on the comet, this vapor collapses back down directly into a solid onto the surface. But it's not just going up and going down and going up and going down. Every time it sublimates away, it can pick up a little bit of surface and carry it away as well. Little bits of dirt and dust get stuck to those bits of water vapor and get carried away. And this is what ultimately is generating the enormous tail that we see on a lot of comets. And what we're seeing is, at least very close to the surface of a comet, that tail is very variable. And it depends on where you're looking and what time of what we call the local solar day you happen to be looking.
So, I mean, we're going to get more new information coming out from Rosetta, I mean, as the comet moves through all of its, its evolution as it sort of gets further and further away from the sun. So, what do all these changes tell us a bit more about what's happening on the comet?
Yeah, that's right. We've been tracking the comet now during its sort of 9-month approach into the sun, and now we're going to watch it move away from the sun. And just like spring and fall on the Earth are different, we expect that the process of heating the comet up and then cooling it back down as it moves farther away from the sun will be different too. And because this is the first time we've really had a view this close of a comet like this, we don't really know what to expect. But after a year of watching 67P become more and more active, we expect that activity will start to decline as the comet moves farther and farther away.
Awesome. All right, I think we have time for one last quick story, David, and this is just so amazing that we have to show this.
All right, let me see if I can screen share this without breaking the internet. All right, cool. This is one of those things when I see, I'm like, why isn't this a huge news story? Because it's so amazing.
It was pretty big.
It was. I was amazed. I was like, well, let me see if anybody's written about it on Universe Today. I'm like, surely somebody's grabbed it. Nobody grabbed this one yet. I just saw it at the right time. This is an actual image of an exoplanet in motion in orbit around the star Beta Pictoris. This is the planet Beta Pictoris b. And the simulation is done over about a 2-year period, courtesy of the Gemini Planet Imager at the European Southern Observatory in Chile. And you can see the occulting mask is that dark bit. You notice in a few years they're going to lose it behind that occulting mask, actually. So it's kind of cool they did this little rapid-fire motion. It's in a 22-year orbit, and you can see the astronomical unit scale at the bottom of the graph. That actually shows how many astronomical. It's in about an 8 AU orbit every 22 years, something like Saturn's orbit in our solar system. However, this exoplanet is about 8 times the mass of Jupiter, so it's very massive. As a matter of fact, when you look at the plus or minus on it, it says plus or minus 4 Jupiter masses. That high end is in the low end for a brown dwarf, so it might be it might not be an. There's a few exoplanets that kind of blur that line that could potentially be a low mass brown dwarf.
Right. So if it turns out to be a brown dwarf, this animation is worthless.
Still, it's still pretty cool.
To be clear, we're not seeing the planet here, right? The planet would be some tiny little dot at the center of that white smear.
Yeah.
So sorry, we're just at the end of the hour, and I know that Maggie's got to go, and so we've taken up her time. So Maggie, we should wrap this up and give you a chance to shamelessly plug some information, and then you can book out.
Sure. So for anybody who's listening who is in the Southern California area, In 2 weeks from now, the weekend of October 9th/10th or 10th, 11th, we're holding the JPL open house here at JPL. So anybody, anywhere can come on lab and get a full tour of JPL, and it's a big event, and we bring out everything, and there's people all over the lab giving tours of the facilities, and so I'll be there on Saturday morning at the Mars 2020 booth, but there will be thousands of people on lab getting a tour, so if you're in the area, you should absolutely come along.
And people should follow you on Twitter, so it's Martian Magster, right?
Yes.
Awesome. You should follow her on Twitter, and then you can get more updates. Well, thank you very much for joining us, Maggie. We really appreciate it, and we hope when we've got some updates, maybe on the 2020 rover, you can come back and give us more information. Thanks a lot.
Absolutely. Thanks for inviting me.
All right, Dave Dickinson, where do we find out more?
Yes, this week I was active on Universe Today. I recently started contributing to Sky and Telescope, which is super cool. And I am offering free chapters of my science fiction on at AstroGuys. You can read free chapters every Friday. There's a new chapter up there right now, so go read.
What is the title of the book that you were sharing?
The one I'm sharing this week is called The Standard of Deviation. It's one of my what I think is one of my better stories. Most writers are pretty self-loathing, so I hate to I'm more critical of my stuff than anything.
It's the least worst.
It's the least worst.
Yeah. So let's say a person wants to just cut to the chase and buy these books from you. Where do we do it?
There's links right on AstroGuys up through Amazon. There's free chapters, and if you can't wait to read these a chapter at a time, you can just go right on Amazon through the links, and it links you right up to my author page.
Or go to Amazon.com and search for David Dickinson, and then just buy all his books.
Yes.
Okay, great. You know what book I think you should do, Dave?
What's that?
You should do something like that one. Night Watch.
There's
Night Watch
definitely
behind
room
me.
for a new edition of that book, if nothing else.
Yeah, and it's written by Terrence Dickinson.
Night Watch. Yeah. Yeah, I'm not a relation, but yeah, I think I've looked at that before. Well, the yearly guide we do on Universe Today is almost morphing into an ebook. It gets bigger.
I know. Let's turn it into a book. We'll talk.
It's one of those blog posts that takes me 6 months to write.
I know. I think it's a book. We'll talk. Morgan, where do people find out more?
Yeah, well, if you want to see me join in with the rest of planetary science and freaking out about every latest Pluto image, then you should follow me on Twitter at Morgan Rehnberg. Otherwise, you can see what I've been working on lately over at morganrehnberg.com.
Fantastic. And Paul, where do people find out more?
They can follow me on Twitter at PaulMattSutter, PaulMattSutter. It's spelled exactly as it sounds. It has I put all my updates for all my writings for space.com, all my podcasts and appearances, everything gets thrown up on Twitter, so it's a good way to follow what I do. If any listeners are in the Columbus area, next Friday for the premiere of The Martian on October 2nd, we're going to be doing a big outreach event at the Gateway Film Center. We'll be there hanging out before the movie, and then after the 8 o'clock premiere, whatever the time is, after the movie, we'll be doing a Q&A session with some astrophysicists and planetarian people from Columbus. It'll be a really good time.
That sounds terrific.
So that's how I was able to get free tickets to The Martian.
Oh, nicely done.
That's how it's done.
Well done. But yeah, I think people should also search for your podcast, Ask Spaceman, right?
AskASpaceman.com.
Perfect. And get big, complicated questions answered in typical Paul fashion. So I think
I don't know if that's a good or bad thing. But yeah, questions that take an hour to answer.
Yeah, that sounds awesome. I love it. Great. Okay, and once again, you can, of course, my website is Universe Today. There you go. This is the world headquarters, in case you were wondering where the world headquarters were. And so for the people who are listening to this on audio and the people who are listening to this on video, and even the people who are just watching this live or watching this on YouTube, if you can do us a favor, we really need your help, which is to go to iTunes and leave a review or leave a rating there, ideally 5 stars, of course. Anything less would be, go ahead and email me and tell me the problems. Yeah, it really would break Morgan's heart.
If you would give it 1 star, why are you even listening?
Yeah, exactly. You hate listening it. So yeah, if you could go, because we don't have a lot of ratings there, and so it just gets buried in a lot of the other things. And we all know that apart from, say, Astronomy Cast and Ask a Spaceman, it's the 3rd best space-based podcast that's on iTunes. And so we really need to get the word out and let people know about it. So if you could take a second and go to iTunes, even if you're just gonna delete iTunes off your computer the second you've done it, and I wouldn't blame you for that. It really is the wise move. That would really mean a lot to us. We really appreciate it. So if you could do that, that would be great. And while you're at it, go ahead and subscribe to this YouTube channel wherever you're watching it. All right, enough shameless self-promotion. Thanks everyone for watching. Thanks to Maggie for joining us, and thanks of course to our panelists. Morgan, next week we want to know what you thought of the lunar eclipse.
I'll do it.
All right. One last thing, of course, is a huge thank you to the WSH crew. This is the community that is joined at the hip with this show. They are really our executive producers, all 500 plus of them, and they're the ones who pick the guests. They're the ones who choose a lot of the stories that we do. We really couldn't do the show without them. And if you want to really be a part of the show and help make the show that you want to see, join the WSH crew. They've now got their own website, which is wsh-crew.com. WSH-crew.net, and they're also at WSH Crew on Twitter, and that is the fans who have turned into the producers of the show. So if you want to be a part of the show, join them, and you can help sort of make the show that you want to see. We are literally just their puppets at this point. So thanks everyone for watching. Thanks everyone for joining, and we will see you all next week.
See ya.